So it's take whatever you like, kind of. Okay. So, and there are so many experiments that have been done. You know, so for instance, AFM, you can do AFM. There's also laser tweezer, so-called laser tweezer. Then there's always magnetic magnetic tweezer experiments. Then you can have biological membrane, all kinds of different experiments in which you can measure the strength of the ligand receptor bond. And this is from the paper, one of the paper in Current Opinion of Structural Biology. And actually, this table is like 5 pages long. So I just I just showed you 1/5 of the table just to show you that there have been so many applications of single molecule methods, applied to biological molecules. Okay, so this method has been applied to ligand to P-selectin PSGL1 pair. So this is the crystal structure. Okay, so for instance, if you look at PSGL1, that's counter receptor. So it's a huge molecule, but the part responsible for binding with P-selectin is this short. So it has some amino acid residues. Okay, so there are many 16 or so amino acid residues, but then there's also a sugar part. So the ligand is like a hand with 2 legs, like a fork with 2 legs. So one is protein, the other one is sugar. So it's glycoprotein. It's very complicated glycoprotein, and you see in here just the small portion of this portion here of this molecule, and the binding is also calcium dependent. So there's this calcium ligand, calcium 2+ in here, and then you have this P-selectin. So P-selectin is this protein here. It has 2 domains, EGF domain, and then lectin domain, so-called lectin domain, and in here, what I showed you is the superposed structures of unliganded P-selectin and the P-selectin ligated with this molecule. And you see in here that there's some structural change associated with the binding. In particular, you have this slight shift, slight movement of the EGF domain, and then the arginine 54 glutamate 74 loop is moving slightly from the periphery to the surface to accommodate binding of this molecule. Okay, so this is the pair that we're talking about. So shear threshold, all these rolling cells on the cardiovascular surface, everything has been reduced just to 2 pairs of interacting molecules in order to find out the molecular origin or shear threshold effect or catch-sleep dynamics, unbinding dynamics. So this was the experiment published in Nature in 2003, in which McEver and Zhu, these were the primary 2 people who have been responsible for carrying out this experiment. So basically, AFM, what you do is you have piezoelectric transmitter, then you have cantilever, and at this cantilever tip you have interacting molecules right here, and then you shine laser here, and then whatever happens to your cantilever tip will be reflected in the number of collected photons in here, in the photodiode. Okay, so this part of the experimental setup is magnified here. So you have this bilayer here, and then you have P-selectins sticking up, right? So these are your receptors. Then cantilever tip. You have counter receptors here, PSGL1, and then so they did they did experiment on PSGL1. This is monomeric form of PSGL1, and then they also used so-called monoclonal antibody against P-selectins. It's called G1. So let's call it PSGL1 and G1. These are different molecules. Okay, they just did it just to show the difference. You have this molecule, you have this kind of interaction, then if you change it and you put this molecule instead, then you'll have something else. So they just wanted to have it in order to compare, okay? So what happens is that when you compress, when you do this, when cantilever tip is approaching the surface, then you press against the receptor, Okay, so that's the compression cycle. So you have, this is the compression cycle, and then once cantilever tip comes close and then presses against the receptor, after that you have tension cycle. It goes up again and applies tension, mechanical tension in this case. So if you have successful binding, then you have reading here, and then during some lifetime you'll have reading, and then reading will disappear. That means that the bond has disrupted. Or you don't have successful binding, then there will be no signal, so it will be just noise level here. Okay, so you can see in here that the instantaneous reading of force is very noisy, but if you do it many times, then you can reduce the noise level, okay, and then you can obtain, this is the running average, and then you can obtain much higher statistical significance. Okay, so you can use simple p-value in order to understand if you have good statistics or you don't have good statistics. Okay, so that's what they have done. And now, if you are a theoretician and then you're thinking about these things, then to describe unbinding, there's so-called Kramer-Smoluchowski-Zwanzig theory of unbinding, and it has been developed a while back, 20, 30 years, starting from the times of Kramers, but then Smoluchowski and then Zwanzig. I read it from Zwanzig book. I don't have a reference to that book, but anyways. So you can view a bound complex as a little ball sitting in the potential well. Okay, this is your potential well. In order to unbind, your little ball has to roll all the way up and then overcome the barrier, and then you have unbound. You have ruptured your complex. So basically, the kinetics of unbinding, you can view as the evolution of a little classical particle on the potential on some potential surface that has more or less harmonic potential well with some barrier. Okay, so therefore, if I don't have force, so then my unbinding rate will be proportional to the product of the ratio of the diffusion constant divided by the curvature of the barrier bottom and of the well, potential well, that's the curvature, L mean, and then the maximum, L max. So that will be your first factor, and it will be exponentially small due to the presence of the barrier height FB. You have to overcome this barrier, and that comes at a price, and the likelihood that you will overcome this barrier is scaling as exponential of minus FB over KT, where KT is temperature. So L min, L max quantifies the curvature, instantaneous curvature of the bottom and top of your potential energy surface. Now, if you start applying force, what's going to happen is it's going to lower the barrier. So, like, you apply some force, it will lower the barrier. You apply more force, it will lower the barrier even further until the barrier disappears. Okay. So every single time you apply force, you change the landscape. You change the energy landscape. Okay. And you give it a discount minus sigma f. So you had initially your barrier FB, and then you have to subtract from that a product of sigma, the distance from minimum to maximum, times f, where f is force. So therefore, if the force is applied, then instead of K0, you will have unbinding rate. K is equal to K0 times exponent sigma f over KT. That's the standard theory, okay, that people use in order to describe unbinding. So if you use this theory, and then what you will come up with is that the average lifetime of the bond must exponentially decrease with force. Okay, and to give you a flavor, of what it is like, typically the barrier heights are few kT, because this is biophysics. We don't have huge energies; we have small energies. Then sigma is from 1 to 5 nanometers. Typically, it's around 1, 2. And then the unbinding forces are from 10 to 100 piconewtons, very small forces.